All right, good afternoon, everyone. Welcome to the Virtual Laboratory Forum for the month of November 2015. This is Steve Smith, your host of the VLab, and I'm joined in Silver Spring, Maryland, with John Chattel, our technical production manager. We are about to begin an interesting session here. Our topic today is the Ensemble Situational Awareness Table, an overview and future enhancements to be presented by Bill Lamberson of WPC and co-authors Trevor Alcott and Chad Kaler. We have heard of the Situational Awareness Table before. I believe Trevor Alcott presented it in a previous VLab forum. But as you may be aware, I'm going to find out shortly, that prototype that was developed by Trevor Alcott is being transitioned to operations within the IDP web farm in NSEP. So per usual at the VLab forum, we're here to present and share things that are in transition or potentially to be transitioned to operations in Weather Service and other parts of NOAA. So our format, remind you, it's approximately 30 minutes of presentation content and then about 30 minutes of question and answer to follow. So we ask that you hold off your questions unless it's an essential clarification to the Q&A part. And also a reminder that the entire session is being recorded and will be uploaded to the VLab Forum website shortly thereafter. So I think without further ado, Bill, are you there?
Yep, I'm here.
Okay, well, why don't you take it away?
All right, thank you for having me. And before I begin, I just want to acknowledge Trevor Alcott and Chad Kaler, who, as he said, have done a lot of the background work in getting the Ensemble Situational Awareness Table up and running, and I have more recently, I guess, inherited it from them, and will be the person who's making enhancements to it from now on. All right, so I'm just going to begin with a brief outline of what I'm going to be talking about today. I'm going to start out with an overview of what the Ensemble Situational Awareness Table is. Then I'm going to go over a couple of case studies that highlight the table's usefulness. Then I'm going to touch on our ongoing efforts to transition the tool to the Integrated Dissemination Program. And then finally, I will finish with some of the scheduled improvements that we have planned for ESAT. So for those who are unaware, ESAT is basically a tool that adds context to the NAIFS forecast that should help a forecaster identify and determine the likelihood of a potentially high-impact weather event. So we all know that ensembles contain extremely useful probabilistic information, but a lot of times forecasters don't have the time to mine through the onslaught of data in search of this useful information. And to illustrate this, I just have a plot which shows the 168-hour gas forecast of 500 millibar heights. This is just your standard spaghetti plot, which oftentimes can be useful, but there's a lot of times where there's just lines going everywhere and it's hard to make heads or tail of this type of plot. So we need a tool that will effectively leverage the ensemble data to point out what is significant in the forecast and how likely this significant event is. And that's kind of why ESAT was developed, to kind of help fill this need. So how do we add context to the forecast? Well, context is added by comparing the ensemble mean forecast to a reanalysis climatology, or RClimate, and a model climatology, or MClimate. And the tool is based on the idea that the ensemble mean can be leveraged as a confidence tool. And by that I mean when the ensemble mean departs significantly from the climatology, it usually indicates that there is agreement in the location and timing of a large event among the individual ensemble members. And then in turn, a large event is usually what follows. So the idea is that a tool that displays how much the ensemble mean differs from the climatology could improve forecasts by first alerting forecasters that a high impact event is possible, and then second, by clarifying the ensemble's confidence in the event. So for those who may be unaware, with R climate and M climate, reanalysis climate will tell you how the forecast compares to typical conditions at this time of year. For example, it can tell us that a trough this deep in November is quite rare. M climate, on the other hand, will tell us how the forecast compares to other forecasts that are made at this time of year. For example, it can tell us that the model rarely predicts this much precipitation at 5 days out in October. So ESAT uses this R climate to come up with several different output types that add context to the forecast. So the first output type we have is standardized anomalies, which just tell us how different the model forecast is from the climatological mean. We also have percentiles, which tell us where the model falls with respect to the climatology. For example, is it just in the 90th percentile, or is it even higher than that and say like the 99th percentile? We also have return intervals, which tell us how often a forecast value shows up in the climatology. And then finally, we have the separate output, which is what we call the probability of an extreme event, which is just the percentage of ensemble members that produce extreme values, or in other words, the value that is outside of the climatology. So to come up with these outputs, what we do is we compare the NAIFS ensemble mean to the 1979 to 2009 CFSR reanalysis. So for those who may be unaware, the NAIFS is just a combination of the GEFS ensemble and the CMC ensemble, or the Canadian ensemble. And this comparison to the CFSR is done over a 21-day window that centers on the forecast valid time. And also it should be noted that forecast valid at 0Z will be compared only to 0Z analyses, 6Z forecast compared only to 6Z analyses, and so on and so forth. So this 21-day window was chosen because it's long enough to highlight events associated with impacts, but not so long that it only highlights the massive events. Because I'm sure, as we all know, you can have a high impact event without having an all-time record. So to kind of clarify further what exactly this 21-day CFSR climatology means, I just have an example that, say the Ensemble Situational Awareness tool is indicating that 500 millibar heights at 0Z on the 20th of November are in the 90th percentile. What that's really saying is that 500 millibar heights are forecasted to be higher than 90% of all 0Z heights in the CFSR between 10 November and 30 November. So for the R climate output, we primarily focus on pressure level variables. So we have those outputs available for geopotential height, temperature, specific humidity, U wind, V wind, and wind speed at the levels of 200, 500, 700, 850, and 1,000 millibars. But we also have a few single level variables, including sea level pressure, precipitation, and integrated vapor transport. For the model climatology aspect of the table, what we do is compare the GEFS ensemble mean to the ensemble mean from the GEFS reforecast data set. So for the model climate, we are only using the GEFS model and not the NAIFS, and that's because we do not have a reforecast data set for the Canadian. So we're kind of limited to the GEFS. So what we do is we compare the GEFS to the GEFS reforecast, again, over this 21-day window that centers on the forecast valid time. And in addition, 6-hour forecasts will be compared only to 6-hour reforecasts, 12-hour forecasts compared only to 12-hour reforecasts, and so on. And then again, forecast valid at 0Z compared only to 0Z analyses, and so on. So for the model climate output, we have, again, we have the standardized anomalies, we have percentiles, and we have return intervals. However, presently we have much fewer variables that this is available for. So for now, we just have geopotential height and temperature on a few pressure levels, and then we have sea level pressure and precipitable water. But I would also like to point out that we have a percentile version of a QPF table, which I find very helpful, and I'll be illustrating that in one of the examples later. So I don't have time to kind of go over all the different outputs, but if you're new to the Ensemble Situational Awareness table, I would recommend that you start out using the percentile output. And that's because not all forecast variables are normally distributed. And the percentiles will help you translate that standardized anomaly into where exactly does this event fall relative to the climatology. So to illustrate this, I just have a plot on the bottom here which shows the probability of various precipitable water values at 0Z in Salt Lake City in January. So we can see that this variable is not normally distributed. There's a significant right tail to this variable. So if we apply the normal distribution, which is what you're doing when you're coming up with a standardized anomaly, you're going to get, or it's going to suggest things that aren't necessarily true about the data set. So for example, according to the normal distribution, about 2.2% of values should fall 2 standard deviations above the mean. But if we look at our actual observations of precipitable water values, we see that almost 4% of the values fall 2 standard deviations above the mean. So this kind of signifies that the normal distribution doesn't always fit every variable, and it can suggest things that aren't necessarily true, and that the percentiles will explicitly tell you where the event falls in the climatology. So to kind of illustrate this, I just have a comparison of the NAIFS mean integrated vapor transport and standardized anomaly, and also the same thing for the climatological percentile for a heavy precipitation event that occurred on October 28th of 2013 in Alaska. So we can see that the NAIFS was predicting a pretty anomalous integrated vapor transport values up into central Alaska, so a wide area of 8 to 10 standard deviations above normal. But still, you're kind of left wondering where exactly that falls relative to the climatology. However, if you look at the climatological percentile, it's very explicitly stated that these values are outside of the CFSR climatology. So that's kind of an overview of what is contained in the table. So now I'm sure some people are wondering where they can get the table. Well, it is available at the site on the top here, ssd.wrh.noaa.gov/SA-table. So if you go to that website, you will be confronted with a screen that looks kind of like this. So you'll have the table on the left here, and then above that is where you can change different parameters, I guess. So you can change your model run, you can change your table region, you can change your plot region, and also you can toggle through the different outputs we have. So once you get that set up to what you want it to be, you just click View Table, and it'll generate the table like this. And then clicking on the table will generate an image like I have here at right. So another thing that a lot of people might be wondering is the table even useful? Because obviously it relies a lot on the NAIFS, so it's only going to be as accurate as the NAIFS is. And some people may question whether the NAIFS is terribly accurate, and then by extension if ESAT is accurate. So the short answer for this is yes, but I would encourage you to go to the above site for a whole host of verification statistics. So now I don't have time to go through all the verification statistics that we have for all the different variables within the table, so I'm just going to show you an example of the verification we do for the standardized anomalies, and then the verification we do for the percentiles. And this is more to teach you how to interpret the plots so that if you are interested, you can go back later and kind of look through the verification website and see what kind of variables you're interested in. So for verifying the anomalies, we have a 4-panel chart that looks like this, where the top left panel just shows the forecast frequency as a function of forecast anomaly for the 72, 144, and 240-hour forecast. So basically, the take-home message from this plot is that larger magnitude anomalies are more common at shorter lead times, which makes sense because as you get closer to an event, there tends to be more agreement between the individual ensemble members, which is one of the primary ways to get a larger anomaly. Then the other 3 panels in the verification plot are these reliability diagrams, which show the analyzed anomaly versus the forecasted anomaly, and then we have the one-to-one line in black here, which goes through the middle of the plot. So you want your forecast to be located along this one-to-one line. So that's signifying that your forecasted anomaly and your analyzed anomaly ended up being the same thing. So that's a good forecast. So we can see that for the 144-hour forecast for 500 millibar geopotential heights, the NAICS does a pretty good job, and on average it lies right along this one-to-one line. And then further, we also have the 10th and 90th percentile verification plotted as well. So if we say, go look at the days when we had a forecasted anomaly of 3 standard deviations above the mean, we can see that at 90% of the points where the day 6 NAICS forecasted anomaly was near 3 standard deviations, the analyzed anomaly was at least 2.5. So that's a pretty decent forecast. So now moving on to the percentiles, again we have a 4-panel chart that will look like this. The top left panel just shows the number of analyzed 100 percentile events for the particular variable that you're looking at. Then over on the right, we have a plot which shows the forecasted versus the analyzed frequency for the various percentiles at the various forecast hours. So basically, the take-home message from this plot is that at longer lead times, the NAICS ensemble mean to under-forecast extreme events, which makes a bit of sense because as you go further out in time, the ensemble mean will tend to wash out a little bit of the signal. So it makes sense that it under-forecasts at longer lead times. Now on the bottom, we have these 2 plots that you see before you. So the bottom left plot can be interpreted as a false alarm ratio, or in other words, when a 100th percentile event was forecast, how did it end up verifying? So if we look at the example of, say, the 144-hour forecast for 500 millibar heights, so when a 100 percentile event was forecasted, we can see that almost 60% of the time, that's what ended up occurring. A 100 percentile event is what occurred. And the other almost 40% of the time, it ended up being a 99th percentile event. So we can see that at least for this variable, the NAICS has a very low false alarm ratio. So the plot on the right here can be interpreted as a probability of detection, or when a 100th percentile event occurred, what was the forecast? And if we look at, say, the 144-hour forecast, we can see that when a 100 percentile event occurred, only about 20% of the time, that's what was forecasted 144 hours out. But we can see that most of the time, it wasn't a 100 percentile event that was forecasted, but still, it was like a 99th to 95th percentile event. So while the probability of detection isn't as great as the false alarm ratio, it's still not that bad. So to just summarize the verification information, the smoothing effect of a multimodal mean can be used to our advantage. So a big signal means that most members agree on the location and timing and large amplitude of the event. And we have, the NAICS tends to have a very low false alarm ratio. So for time reasons, I can't go through the verification for all the different variables that we are verifying. So I'm just going to give you a rough estimate of the NAICS predictability limits over North America for several important weather features. So for major upper level patterns, it's about 8 to 10 days. For major surface highs and lows, it's about 6 to 8 days. For significant warmth and cold, it's about 5 to 7. Strong large-scale winds are about 5 to 7. And significant rainfall events are about 3 to 5. So now I'm going to show you the first of the 2 case studies I have that kind of illustrate the tool's usefulness and how maybe it could be used in an operational setting. So the first case we're going to look at is the Pacific Northwest windstorm from 29 August of 2015. So this was a pretty large event. It caused 2 fatalities in western Washington. At the storm's peak, there was over 300,000 customers without power. There was widespread wind gusts of 50 to 70 miles an hour. And also, it was the strongest summer windstorm to impact the Pacific Northwest in recorded history. So how did the table do, and by extension, the NAICS do with this event? So on these next series of slides, on the left is going to be the table for the Northwest U.S. And then at right here is going to be the mean 850 millibar wind speed in knots, and then the percentile forecast valid at 18Z on the 29th of August. So we can see this is the table for the forecast issued on the 24th of August at 12Z. So if we look at the table during the period of interest, there's nothing really jumping out at us. And then again, if we look at the graphical representation, there's kind of a weak signal for a high wind event, but there's nothing really jumping out from the table. And this is probably because there's a lot of spread that's presenting a large magnitude signal. However, if we step forward just 24 hours, we can see that this is when the NAICS, and by extension, the table really kind of latched on to a high impact wind event for the Pacific Northwest. So now in the period of interest, we can see that there's some maxes showing up in the table indicating that this is outside of the climatology. And then again, if we look at the graphical representation, we can see that it's focusing on western Washington and Oregon, and then the central part of Washington. And if we go forward 2 days to the forecast that was issued at 12Z on the 27th of August, we can see that the table is really lighting up, and it's really indicating that this could be a high impact wind event for the Pacific Northwest. And then again, if we look at the graphical representation, it further hones in on that area of western Washington and Oregon, and then into the central part of Washington. And as we get even closer, the forecasts get even better. So this next slide, I'm just going to show you the comparison of those various forecasts. So the 126-hour forecast, 102, and then 54-hour forecast, along with their verifying analysis. So we can see that the table and the NAICS did actually a pretty decent job with this event. So this next study, or this next case study, is going to highlight the QPF aspect of the model climate table. And I'm going to show you the case study of the Texas and Oklahoma flood of 24 May 2015. And this is the event that caused that massive flooding in Wimberley, Texas. So I just have a figure which shows the 24-hour precipitation ending at 12Z on the 24th of May. So we can see a large area of 2+ inches of rain from Oklahoma extending down into Texas. So how did the table do with this event? Well, it's another case where the table did quite well. We can see that 4 to 5 days out, the table is indicating that the NAICS mean forecast is completely, the NAICS mean QPF forecast is completely outside of the model climatology. And then if we look at the reforecast, or if we look at the graphical representation of this, we can see that while the amounts are displaced too far to the west, it is indicating that Texas and Oklahoma should be on alert for a potentially heavy rainfall event. So as we get closer to the event, the table still highlights that this is the maximum in the reforecast climatology, and then the area of heavy rainfall kind of shifts east closer to where it actually ended up verifying. And then as we go forward again, so this was the forecast that was issued by the NAICS right before the event. It pretty much hones in on Oklahoma into central Texas as being the areas that could be impacted by potentially historic rainfall. So like that other slide, I'm just going to show you a comparison between the various forecasts. So this is about a 5-day forecast, 2 to 3-day forecast, and then right before the event. We can see that the Ensemble did a pretty decent job with this event. It started out having a location that wasn't quite right, but then it corrected to be in the proper location. So just to summarize the case studies, the Ensemble Situation Awareness Tool provided a approximately 5-day heads up that an extreme high-impact weather event was likely, and the tool visually communicated this information in an efficient way. So now that I've kind of introduce you to all the great things about the tool, I would be remiss if I didn't mention a few of the caveats. The first caveat is that the Ensemble Situational Awareness tool uses a 21-day window, so maxes or min forecasts are rarely all-time highs or lows. In addition, not every high-impact event is associated with anomalous upper-level forecast fields, but at the same time, anomalous upper-level fields are not always associated with high-impact weather, so those are two things you need to be keeping in mind when you're looking at the table. And then also, not every high-impact event is well predicted, and the tool obviously will struggle with these events, because if you have a bad forecast, the tool is not going to help you. So in summary, the tool may not provide a heads up for every high-impact event, but when it is indicating a high-impact event, you should pay attention because it's probably going to happen. So now I'm going to get into some of our current work on the Ensemble Situational Awareness tool. So we are currently in the process of transitioning it to the Integrated Dissemination Program, or IDP. So this will allow for enhanced stability and support for the tool. So this transition process is underway, and version 1 will hopefully be available by February of 2015. So version 1 will just maintain ESAT's current functionality, and the only improvement will be the addition of table and plotting domains for all NWS county warning areas. Because as of now, there are mainly only plotting domains for CWAs that are in the western region. And also, we're currently developing some training material for the tool. So I think we're just going to start with me kind of testing it out on the forecasters here at WPC. And then eventually, I would like to get something done through the Warning Decision Training Division. So hopefully, you can look for that a few months down the road. So for our future work, version 2 of ESAT will tentatively contain the following major enhancements. So we are going to add more regional domains and domains that cover the Pacific and Atlantic Oceans. We are also planning to add a 91-day climatology functionality, which will be in addition to the current 21-day. We are going to add more variables, focusing on surface variables such as 2-meter temperature, 10-meter wind, and CAPE. And that's because the upper-level anomalies may not be associated with surface weather that's high impact, which is what people are most concerned about. And then also, we would like to have a version of ESAT for the ECMWF Ensemble. And right now, version 2 has a tentative release date of summer 2016. So these enhancements for version 2 are not set in stone, so if you have an idea or want to see something in ESAT, please let me know. I'm all ears and would love to hear. So that's basically all I had to say. And with that, I guess I will take any questions or comments. So thank you for listening.
Thanks, Bill. Excellent overview, very thorough and comprehensive. Appreciate you going through all of that. So at this point, if you're in the GoToWebinar and like to ask a question, we'd ask that you use the raise your hand feature, and John Chattel will unmute you so you can ask your question to Bill directly. Or you can use the chat feature as well, and John can relay your question to Bill. Do we have any questions yet?
Yes, Zoltan Tom would like to ask a question.
Zoltan, are you there?
Yes, do you hear me?
We do. Go ahead.
Okay. Hi, Bill. This is a great presentation and very nice work. Thank you very much. I have one question or comment. The question is, you are determining the percentiles the way you described to us using the reanalysis and the NAIFS forecast. Is that correct?
Yeah. So the percentiles for our climatology are using the CFSR, and then for the model climatology, we're using the GAPS-free forecast data set.
Yes. Yeah, thank you very much. I'm not sure if anyone is on the line from EMC, because what I like to, the comment is that operationally, the NAIFS post-processing, there is a statistical post-processing infrastructure that was set up 8-10 years ago with NAIFS, and that post-processing that contains a bias correction element that is somewhat related to what you do in terms of model climatology, evaluating the forecasts in terms of model climatology. You do that to account or correct for model biases, lead time dependent biases. That actually is done explicitly as a bias correction step. So you can access bias corrected NAIFS forecasts. So that's one comment. And the other comment is beyond the bias corrected NAIFS forecasts, and those are available for 80 or so variables, I believe, near surface and upper level variables. Beyond that, NAIFS also determines on the order of 20, for 20 of those 80 variables, climatological percentiles. So again, as part of that post-processing, NAIFS post-processing, percentile grip files are generated with the percentile, climatological forecast percentile information. So that's something that you may want to actually look into, how you may be able to benefit from all that information that is churned out for the have been produced for the past 8-10 years, day in and day out. Thank you very much. Again, very nice work.
All right. Thank you for that comment. Thank you. I did not know that.
You may want to contact Eugene and Zhu about file names and what's produced and all that.
Okay. Thank you.
Thank you.
Thanks, Zoltan. John, do we have another?
Yes, Eugene Brusky would like to ask, are there any plans for a dprog DT capability to more easily identify trends?
No, that's not in the plans now, but that's something we can look into.
All right. Gene, did you want to follow that up with a follow-up? Did he?
He has not typed any additional
questions. Okay. Do we have another question?
No, we don't.
In the room, do we have a question?
I would just like to take a look at what, in about the middle of the presentation, there was like a 2D table with different colors in the different cells. Could he bring that up again? Yeah. Like, well, no, back when it doesn't say max so much. Yeah, like that. What is C? Okay.
So yeah, on Bill, a clarification for the table. This is only based on the table entry on the model comparison to the model climatology. Is that correct?
Yeah, this one for the QPF is just comparison to the model climatology.
Okay.
Is each forecast, is each column, are they all forecasts for the same time from different times back?
There,
like
if you look at, right, okay, so if you look at the top here, it's for a 6-hour forecast, 12-hour, 24, 48, and 72.
At
so
the same verification.
Lengths.
Sorry?
It's just for different lengths of time.
Yeah, different times back. Okay. And is that for just one point, or is it for numerous points?
The table displays the maximum value that was in the plotting domain. So, for example,
so it's a region.
Right. The
it's
table
a regional.
Is for Texas.
Okay. Okay. We have a question from Bob Vaughn.
Yeah, that's something that wasn't clear to me until I think the very end. All of these values are summations over some area, and the area is what you just now called a plotting domain. And so all of these maxes and so forth refer to that particular domain, right?
Right. Well, it's not an area. What's displayed in the table is just, if you look at the plotting domain, it's just going to pick out the maximum value, and that's what's going to be plotted in the table that corresponds to that plot. Does that make sense?
it's a worst case
Right.
over a large domain?
Right. So
Okay.
if on the one we have up here, most of this image is not showing a max, but what's going to appear in the table is a max because there's 1 or 2 points that have it. So it just picks out that point with the maximum percentile, and then that's what goes into the table.
So it's surprising your false alarm rate isn't higher given that. That surprises me. But anyway, could you flip forward one more slide on this one? Yeah. So now you know, looking at the table again, and you've circled in red ellipse there the area, the time frame projections you're interested in. But then if I just if I mentally removed that red ellipse from there, and then I looked at your cyan maxes. So how do you interpret the maxes going to the longer projections? Is that related or not related?
Well, this column contains the QPF that occurs over a 72-hour period. So even though we're a few days after the event, it's still going to catch it. Does that make sense?
I'm not sure.
So like this is showing that it's a max of a 72-hour QPF total. So even though the event is only 24 hours long, here we're still looking 2 days or 2 or 3 days backwards, so we're still going to catch that event. Because if you notice, they don't extend very far past the ellipse if you look at, say, just the 6-hour. Because that's just a 6-hour QPF total.
Okay. Okay.
Does that make sense?
Yeah, I think I'm getting it now. But the image to the right is, let's see, that image is a 48 to 72 hour forecast. So is this what you would see on the table display at the website?
Yeah, so if you clicked on, I guess, the one that would if I clicked on one of these maxes, I'm not sure which one, but one of those would generate that image.
Okay, so you got to click on the table and you're going to see a corresponding image. Okay.
Right. Correct.
All right. All right. So a follow-up question I had was on.
Steve,
yeah.
I think John Brooks wanted to chime in on that.
Go right ahead. I'm muted.
Yeah, hi, this is actually Andy Edmond. We're together here on this phone. Let me address the last question and try to help out John here a little bit. Don't get carried away with the table. The whole idea behind the table is it's showing the maximum either positive or negative value that you're seeing on that image that's displayed. It's just meant to be a heads up because when you first bring up the table, you'll see, across height, temperature, winds, moisture, IVT. So that table is nothing more than meant to just get your attention and say, oh, maybe I should go look at that graphic a little bit more. The other thing I want to sort of point out to everybody, we've been doing this in Western Region now for a number of years. Don't get tunnel vision. Don't be looking at, well, what's the number in my backyard or at my ASOS site and my CWA. The whole idea here is to be looking at the trends and the features and how they're evolving. So in the graphic that you were just showing, the screaming message is, if I'm a forecaster, hey, the models are producing some the Ensemble forecast is producing a really interesting forecast. They don't often do this. I ought to be paying attention to this event and digging in deeper. So that's the whole point with this. It's not to give you the final finished answer. It's to tell you what collectively a whole bunch of Ensemble members are trying to tell you. So look at the fields, look at the graphics. Once that table gets your interest, dig in further and look at what the fields are and how they're evolving.
Okay, thanks, Andy.
If I could say one more thing, when you take a look at the verification, that the screaming message is, when the ensembles agree and it's a big event, it's chronologically significant, a big event, there's pretty darn good skill. And if you could bring up like that verification slide, it sort of shows that. So, you know, when ensembles are all over the place, then there's not much skill. The tables aren't very useful. But when you start to lock onto a big signal, roughly 9 times out of 10, you can really sort of buy in that something big is going to be happening 7 days out or 4 days out or whatever. There you go. That slide shows it really well that, you know, when ensembles lock on to like a 2 or 3 standard deviation big change, yeah, I'm going to make up a number here. Let's say they're forecasting a 3 standard deviation significant change for your general area. Yeah, what might actually verify might be 2 or 4, but, you know, what's not going to verify is a ridge. So, I mean, again, this is a situational awareness tool. It's how do you mine information out of 20 or 30 ensemble members to sort of get the information needed to improve your DSS messaging. And I'll stop right there, guys.
Yeah, Andy, well, don't go away while you're still there, and Bill can comment. I mean, so it strikes me that the methodology applied here to the NAIFs could be equally useful to looking at deterministic runs, in particular, like the HER and that sort of thing. Am I off base in that? I mean, this strikes me as more general in use of NWP forecasts and interpretation of NWP forecasts. Is that true?
Yeah, I think what you're seeing here, you know, I'm an old timer, you know, and when I started, you know, you looked at 500 millibar heights and you looked at the precept and you know, off a 4-panel facts chart, and you sort of said, okay, here's what the forecast is going to be. There's a set of emerging tools where we can compare the model performance to either real cometology or the model cometology and start to say, hey, when is it really different? And the whole idea behind this was, you know, for 10 years we've been running ensemble data, but how do you look at 20 or 30 members intelligently? And this was, you know, again, this technique grew off the shoulders of a lot of people, Rich Grum, Randy Graham, Chris Malcolm, the Salt Lake office. We took it and sort of ran with it here even further. But it's the second generation of how do you mine information out of the models and do it intelligently. Yeah, this could apply to regular deterministic models, but I'm much more excited about how we do some sort of second generation work. For example, when you run a deterministic model, you can run time-lagged ensembles where you compare the last run, the previous run, and the run before that, and start to say, where these fields really become anomalous? Where should we really be paying attention? So it's just one of many tools that are out there that should help us as forecasters be use a little better science in how we're looking at the model data.
Okay, thanks, Andy. Bill, did you want to comment on that?
No, I mean, I think you pretty much covered it.
Bill, you did a great job.
So let me ask another question. Where do you start with this whole thing? Do you have a map over the whole U.S. and you look at that map and you find an interesting place, or do you have a table that pertains to the whole map, and when you see some maxes, then you click on the max and then you get the part of the map that pertains to that max and look at that? And so I guess the question, where do you start?
Yeah, hold on one second. All right. So if you go to the web page, you'll get this right here. And so we have both a table region and a plotting region. So right now it defaults to the Western U.S., but there's a whole bunch of different table regions that you can pick, ranging from North America down to just your forecast area. And same thing for the plotting region. So you can kind of tailor it to whatever you say. So if you're, you know, just a forecaster in your county warning area, we would suggest maybe changing the table region.
Can you do a demonstration on the web?
Oh yeah, I can do that.
Why don't you do that? That might make it easier.
Yeah. Okay. Hold on. I'm going to switch to the web, and just.
Okay, the first thing you do is pick a table region.
Yeah,
pick a region.
but wait, before you do this, so these are like predefined, right? So you're going to select them when you go in.
Right. So yeah, you have all these different regions that you can look for the table, and that'll be the maximum in that region is what will be plotted on the table. And then for the plot region, that can be separate. So when you click on that, you will get an image for that, whatever plot region you suggested. So right now, I'm just going to pick a table region for Weather Forecast Office, AFC, and I'm going to pick the plot region to be the continental US.
Bill, we're not seeing anything right now.
All right, hold on. Oh, okay, hold on. I got to switch this.
Okay, but the bottom line is where you start is to pick a region.
Right. So you have to pick your table you have to pick your model run, pick your table region, pick your plot region, pick your output, and then you view a table. Are you guys seeing it now?
Not yet.
No.
Did you relinquish your presenter?
I don't think I did. I have it set to show the main screen.
Yeah, we're just seeing. Oh, here we go. There we go.
Okay.
We see it.
All right. I guess I had to push play for some reason.
Beautiful. We can see it.
All right. So right now I have my table region selected to be forecast or WFO AFC, and my plot region to be the continental USA. I'm going to change it to the percentiles because that's what I prefer. And so I'm going to view the table. And there it generates the table. And now if I click on it, say, might take a little bit, but then it'll generate the image. There we are.
It'll fly when it's on IDP.
Right, yeah. Anyway, so the 2.5 is just the maximum value that's in this particular forecast area. And then when I click on that, because I picked my plotting region to be the continental USA, I'll get a plot for the whole continental USA.
But so, since all of these things are done point by point, you really have a whole U.S. map to start with, don't you?
Bob,
I mean, could you display
the software
the whole
allows you to do anything you want.
Okay, but I'm getting back. I'm getting back again to where you start. It seems like to me that if you had a U.S. map with all of this stuff on it, it would jump out at you what the plotting region should be.
Yeah, I think Bob's looking at a more efficient use case. You know, so if you started large, then you could see the whole thing. And
okay, the software allows you to start for the Northern Hemisphere, North America, the CONUS, your backyard. I like to start, you know, with the larger scale and look at some of how the bigger patterns are evolving. That's where I like to start. And the table sort of highlights you what elements that you want to go look at. You know, for example, when we talk about winter storm, a winter storm isn't always necessarily snow. It might be cold or wind is the screaming message. And for example, the storm that we have currently going through the western U.S. right now, it's really the wind that's sort of the big deal with that. But we built in a lot of flexibility. Bill likes to use, you know, the table you have up there right now, I like to use return intervals. That's sort of the way I think. But there's a lot of flexibility. We purposely built this with a lot of flexibility to allow a forecaster to look at it in a way they like to think about it. You know, I grew up under Len Snellman, and Len Snellman says you start out at the large scale and you at the larger domains and you dive into it.
okay, other questions? Do we have any online, John?
Yes, Daniel Melendez would like to ask a question.
Go ahead,
Yeah.
Daniel.
Thanks. So the table is in a predefined region, and it is it's scaling to what it sees in that region that you select, right? And you can do that independently of the plot, I guess.
Yeah.
What I'm getting at is that you have all these scalable sizes for the values that are populated in the table, and that's user defined, right?
Yeah, correct.
Okay. All right. Thanks.
All right. Any other questions, John?
Yes, Daniel Neitfeld would like to ask, one point to make is that this is a very popular tool in operation, so it's proven to be effective and efficient.
Dan Netfield, I believe, is was involved. He's involved with the extreme precipitation project as well. So this is already operation. It's already demonstrated its popularity and usefulness in the field. So this is moving into the solid IDP infrastructure is just going to solidify its future and allow for new enhancements, some of which you've already touched on for your version 2.0. So coming hot and heavy here, the first version is coming out in February, hopefully, and then right on its heels, wait a minute, February 2015, that must be February 2016, right, Bill?
Yeah.
Yeah, okay, it's coming up in February, and then right in the summer next, hopefully we'll have version 2.0. So people can contact you directly to provide suggestions of other things that might be included in either 2.0 or a further version down the road, right?
Yes, please. I would very much enjoy that.
All right. Excellent. All right. So I want to thank Bill immensely for this update on a very important project. Thank Andy Edmond and Trevor for the early work and continuing to work with this. This is another project that's come to fruition, or it's moving into an operational environment under the new headquarters organization funded by SDNI, and that's great. So I think this is examples of some positive R2O. I think in the old days this might never have gotten to where it's going now, so I think progress is being demonstrated here. I want to remind folks that this will be uploaded to the forum webpage shortly after we finish here. And coming up in December, we've got another field-driven R2O project funded by SDI, an update on the Damage Path Toolkit project, Joshua Scheck and Paul Kirkwood. In January, we're going to hear about the Warp Hydro implementation. February next year, we're going to hear about Insight. March, Tropical Cyclone Tool, Jonathan Blaze, and then in April, a very interesting project, the USWRP project refinement and evaluation of the automated high-resolution ensemble-based, there we go, ensembles again, hazard detection guidance tool for transition. That is a GSD-led project. Very good stuff coming up. So mark your calendars, and we'll see you all in December. Thank you.